Hi, my name is James. In this project, we studied whether benchmark performance can explain why some AI models are more expensive than others. As cognitive science, machine learning track, and data science students, we frequently rely on large language models in both our coursework and research. However, access to these models is often limited by budget constraints. This motivates us to investigate whether the price of LLMs is justified by their performance. We have the following research question: can benchmark performance across different domains, including reasoning, coding, maths, and general knowledge, reliably predict the token price of AI language models? Then we propose the following null and alternative hypotheses as shown. We downloaded our dataset from this large language model leaderboard website as shown. In this dataset, each row is a model with benchmark scores and API token pricing. During data cleaning and processing, to prepare our dataset for modeling, we first removed columns that were not relevant to our research question. We then focused on features with relatively few missing values and dropped rows with null entries to ensure consistency. Finally, we removed columns that contained too many missing values to avoid introducing bias or instability into our models. Then for EDA, our goal was to get a sense of the shape of the data, the range of model performances, and whether or not there are any obvious patterns between benchmark scores and token pricing, and hence draw and predict a possible correlation. We generated many plots, and here are three examples. As you can see, the blended token price distribution, assuming a 3-to-1 input to output token ratio, is heavily right skewed, meaning that most models are relatively cheaper with only a few very expensive models. When we examine scatter plots for benchmark scores, such as HLE, which stands for High-Level Evaluation Score for Advanced Reasoning, versus blended price, we observe no clear or consistent relationship. Finally, the pair plot shows that benchmark scores are strongly positively correlated with each other, indicating that models performing well on one benchmark tend to perform well across all others. Because benchmark scores are highly correlated with each other, this also introduces multi-collinearity, which may limit the predictive power of regression-based models. We evaluated three predictive models: support vector regression, random forest regression, and gradient boosting regression. Among all three, random forest achieved the best performance with an R-square of about 0.24, followed by gradient boosting at 0.21 and SVR at 0.16. Although random forest performed the best, all three models show relatively low explanatory power overall. This indicates that benchmark performance alone provides only limited ability to predict token pricing. In conclusion, although we tested multiple predictive models, their explanatory power remained low, with maximum of R-square of about 0.24. This indicates that benchmark performance alone does not reliably determine token pricing. Instead, factors such as market strategy, infrastructure costs, and provider positioning likely play a more dominant role. For users with limited budgets, this means that higher price does not necessarily guarantee substantially better performance. Thank you.